Okay, so we have a fourth equation in friction problems. And then in this problem, we looked at this block, and if P was large, the block could slide up. And if P was small, the block could slide back down. So we had to analyze it in two different ways. And the only thing that was impacting it is really whether you're analyzing going up or down, the only difference is the direction of the frictional force. So Myra, when we analyzed it for the block sliding up, which way did the frictional force go? Okay, maybe she's not there. Mackenzie, when we were raising the block for it to slide up, which way did the frictional force direction go?
The friction slid down.
Down, right. And then keep going, Mackenzie. And sliding down, which way did the frictional force go?
Up.
Right, great. Okay, then yes, up, thank you. And then the second problem we did, we had the cylinder that had a block on it and had a weight called WB, the weight of the block. We also knew the weight of the cylinder was given. It's frozen.
Yeah, Joanne, you seem to be lagging behind a few seconds. I'm wondering if you're having internet issues.
Okay. All right. What should I do?
Are you able to get closer to the router? Are you far away from the router because you're in a different room today?
Yeah, I guess I could head into my mom's bedroom. But then it's going to take me a while to set all up again. I'd rather do this. I'm going to become the host. Let's see how we do this. How do I change the host?
From participants.
Okay, could you hear me? Yeah?
Yeah.
Yeah.
You stayed downstairs. Anyway, all right, we'll do this. We'll deal with this another way. Okay, so the second problem we had was a cylinder that had a weight of a block on it. And we also got other specifications. And again, we had to decide, is this going up or going down? And we decided that it was going down, which again, what would that control? So Marcine, if we decided that the cylinder would slide down, what did we decide? What would be, which direction do we have to put the frictional force?
If the cylinder's sliding down,
Yes.
the frictional force goes up.
Okay, and we analyzed it. And then I remember someone, probably Jason, asked, well, what if it's going up? So I redid the problem, and I can post the solutions if you want, but I basically did the whole problem over again. I put the frictional force in the other direction. I assumed movement going up. I put the frictional force going down. And what did I get in the end? What do you see in this box? My frictional force is what?
-500.
A -500, which means the frictional force is going the other way, and it only has the potential to move down. Okay.
Because in that situation, it could either slide down or it could roll up, but in either case, the frictional force is going up. Yeah.
That's correct. Right. Okay, good. Okay, so now we're on the third problem, and the third problem we didn't do yet. So this is what our third problem is. So we have a person and we have a refrigerator, and we're given some dimensions. And we're given actually all the dimensions. The width of the refrigerator is 3 feet. The distance to the center point is 3 feet. And then the distance to the person where they're pushing, where the load is 4 feet. Everybody could see that, right? Everybody good? Do I need to pin something or you're taking care of that?
We can do it. Yeah, we can
Okay,
pin
great.
it.
Okay, then I'm also giving you the weight of the refrigerator, the weight of the man, and then the coefficient of friction for both between the refrigerator and the floor and the men's shoes in the floor. And the question asks, can the man move the refrigerator by pushing? And if so, does the refrigerator slide or tip? Okay, so the question is, can the man move the refrigerator by pushing? And if so, does the refrigerator slide or tip? Okay, so now we're gonna need to do this individually as I'm doing it as well. So let's make up a table. Okay, and we really have two bodies here, right? And we may have to analyze them both, but let's just make a table: force, magnitude, direction. So what forces do we have present? So Matthew, I'm doing all the M's. Matthew, what forces are present?
Well, we have gravity force of the two bodies with the mass.
Okay, and let's, instead of calling it gravity force of the mass, let's call it the one word engineers like to use.
Weight.
Right. Yeah, so let's use weight. So we have weight of the refrigerator, which we know the magnitude and the direction, and we have the weight of the man, magnitude and direction. Great. Matthew, you want to keep going? What other forces do we have here?
We have the man pushing against the refrigerator.
Okay, so let's call that P. Okay. And do we know the magnitude?
I don't remember if that was in our givens or not.
No, it's not. Yeah,
Okay.
sorry, I had to take the picture away. So the magnitude isn't given, but we know the direction, right? Okay, what other forces? Keep going, Matthew.
Then we would get a frictional force from the refrigerator.
Okay, so I'll call it sub R. Okay, and do we know it?
No,
No, how about the direction?
we know the direction.
Yeah, and if the refrigerator, which way do you expect the refrigerator to go, Matthew?
Well, it would be moving to the right,
Correct, so the frictional force is going to go
to the left.
to the left, okay. What other forces do we have present? I
We
think
also
we
have,
frictional force of the man, right?
yep.
And we don't know that value. And now I
Mhm.
tried to explain this, and maybe you guys tried to move the refrigerator on a slippery surface the other day and realized that if you can't move it, which way does the man go, Matthew?
Man goes to the left,
Right, so the frictional force would go
to the right.
to the right. And then there's two more forces. What else do we have?
I don't know.
Okay, so think about it. Whenever things touch a surface, what do I need to account for?
Friction.
Right, we got friction. What else? You're gonna laugh at yourself when you hear it.
You like something with the moment?
The normals.
Normal. Oh, yeah.
I knew you would freak out. So N sub R for refrigerator and N sub N for man. And we
Oh,
don't know,
duh. It's,
but we know the direction.
yeah.
Okay, so this is what we have. We have the weight of the refrigerator, weight of the man. We have the P force that the man is putting on the refrigerator. We have the two frictional forces and we have the two normals. Anything else?
I think that's it.
Okay, great. So how many unknowns do we have? 1, 2, we have 5. 5 unknowns. We need how many equations, Matthew?
5 equations.
5 equations and how many bodies?
For 5 equations, 2-dimensional, I'd say 2 bodies.
2 bodies, great. And what do you think those bodies will be?
The refrigerator and the man.
Great. Okay, so how about everybody draw a free body diagram of both of those, okay?
Joanne, will there be a reaction to P? the man pushing the refrigerator, right? Isn't there something that goes back on that?
Correct, and that'll be equal and opposite, right?
Okay.
So it'll still be P. Great point.
Okay, yeah, thanks.
Joanne, can you put that, the paper back up? Yeah,
Yeah.
thank you. And then
Joanne,
back
I have
up at the free body, or not free body, just the overall diagram.
Can you see that?
Yeah, that's great, thanks.
Joanne, I have a question about when they ask like what when the question, I don't understand what they're asking for, or like I understand what they're asking for, but I don't understand what it would be in the symbols, or like what you would.
Yeah, Maria, I find friction problems aren't very clear in their question, all of them. So you'll notice that some of the questions I actually changed the questions for in the homework. So it's not always clear. And what I resort to is doing the regular statics problem and then find, like when I first saw friction problems when I was a student and they asked for a minimum and maximum, I was like, what are they talking about? Minimum and maximum. But then I solved the problem and I got two different P's, like in the sliding the block. And then I was like, oh, that's what they mean. They mean when it's static, what is the minimum value and what's the maximum? But I didn't understand it to begin with. And the same thing with this. It says, can the man move the refrigerator by pushing? Well, if so, does the refrigerator slide or tip? And it's a little confusing, but let's just go ahead and do the statics. And then, I mean, normally you want to know what the question is and what it means to answer it, but you're going to know how to answer it once we get the answer. Okay. It's just, I find them confusing too. It might just be the verbal, and maybe sometimes I'm not, I don't understand words, I'm better at math. So let's just keep going, okay?
Okay.
So we have the person and we have the person and we have the refrigerator. So draw the free body diagram of both.
For the normal force for the person, do you put it on both legs?
I would just stick it up the middle.
Okay.
Just put it as one. I mean, you can split it twice. Sorry, Jordan. You can split it in half, but I would just call it one end. Put his legs together and then put it on his feet.
Yeah, whenever there's a complicated object like the bikes and stuff, I just draw a square. Or like a rectangle or something.
Good. Okay, so the weight of the man, 150. So I'm just drawing the free body diagrams, you guys.
Do we just assume the weight is at 2 feet?
Say it again.
Do we just assume the weight of the man is at
His center.
his center? I can't remember how tall he is.
I don't think we know. No,
I think we said 4 feet.
We just know the 4 feet is to his hand where he's pushing the P.
Okay.
Okay, so okay, here are my two free body diagrams. Did I leave anything out? I should ask in a positive way. Is everything there? Edgar gave me the thumbs up. So did Laura.
Actually, do we
Okay,
know
ready? I'm going to pull it away now.
Joanne,
Yeah,
do we, know,
Edgar.
do we know the width of the refrigerator?
Yes, it's, oh boy, I just ripped it. 3 feet.
Okay, thank you.
Thank you. Yeah, good point. I did forget something. That was critical. And once I do moments, I would realize I messed up. Okay, so let's look at the refrigerator first. Okay, and I'm going to analyze it for sliding, which is what we've done so far. We've analyzed 2 friction problems, both for sliding. So where are we? Matthew, Myra, Mackenzie, Marcine, you went already. Victoria, what equation do you want to use first on the refrigerator? Okay, not here. Okay, Jack, what equation do you want to use first on the refrigerator?
I'm not sure.
Okay, so take a look at the picture and of the refrigerator, and what equation could I use to solve for an unknown? Some of the forces in the X or some of the forces in the Y?
Maybe
You can pass if you want to pass, but I think you could get it now that you see it.
in the X, maybe because you have. Weights.
No.
I'll pass them.
Okay. Let's go to David Lopez.
Some of the forces in the Y.
Yeah, so it's NR minus WR equals 0. So the normal of the refrigerator is 180 pounds. And then I could put in the frictional force. It's, and mu for the refrigerator is 0.25. And then I'm going to do sum of the forces in the X. P minus FR equals 0, P equals 45 pounds. Just check that with my solutions. Yeah. Okay. So first I did sum of the forces in the Y because I knew the weight of the refrigerator, so I could solve for the normal of the refrigerator. They gave me mu, and now I knew N, so I could find the frictional force in the X, right, which is in the X. And then I did sum of the forces in the X, and I got P is equal to 45. So Maria, we just learned that the refrigerator is in static equilibrium for 45 pounds, and I analyzed it for the refrigerator going up. Tell me how the refrigerator could move. What P would I have to have for it to move in that direction?
Greater than 45?
Yep. So if P is greater than 45 pounds, refrigerator moves, I should not say move, I should say slides to the right. Okay, everybody good? So that's for sliding. I just found out what the P is. But do you see another equation? What's another equation? So actually, I got the M's. Dave, even though I solved for these unknowns already, right? Even though I solved for these unknowns already, don't we have a fourth equation that we could use?
Yeah, we could do moment around that point A.
Okay, so now, and let me write A.
It's, yeah, I think it was in the diagram. It was the bottom right.
Right. So point A is right here.
Yeah.
Okay, now you guys, this is another critical thing in friction problems. Dave, I'm going to have you take this on. Right now we have the normal here. If this refrigerator starts to tip at A, where is the refrigerator really touching the ground?
Ah, okay. So if it's only touching at A, the normal's at A.
That means we have to redraw the free body diagram for tipping. And I mean, if you don't want to draw, look, hang on a second. Rather than spending the time drawing it, how about we do this? For situation 1, my normal is here. For situation, or I should say for, let's say for sliding. For sliding, my normal is here. But then when I do tipping, so keep one free body diagram. Let's not spend more time drawing a free body diagram. What I did is I put N for the refrigerator for sliding is here, but N moves to here for tipping. Does that make sense to everyone?
Yeah, I have a question. It's just the normal force is always going to be straight up because of the ground, right?
Correct.
It doesn't matter that the fridge is going to be moving like
It
this.
doesn't matter that the fridge, because remember, this is one of the first things we mentioned. The normal is always drawn perpendicular to the surface. So even if the refrigerator is like this is my surface, and the normal has to be drawn perpendicular to it. Okay?
Now the weight's still coming down from the center.
The weight is still coming down from the center, but it's just about to tip. So the weight you could still keep in the center. That was a really good question. You guys, it's not completely tipping. It's like just about to tip. So you got to move the normal over, but the weight is still here.
Limit as the refrigerator approaches tip.
Yeah, okay. Yes, if you want to say it in math wise. Okay, so now for tipping.
I don't think that would actually go over well in a math class.
Okay, well, whatever. It's fine with me.
Yeah, don't do that.
All right. So you guys look, I wrote sliding and I did all my equations for sliding. And now I'm doing tipping. Jordan, what equation do you think you're going to use for tipping? Think of what tipping is.
Moment.
Right, the moment equation. And where do you want to do the moment about?
I would like to do the moment about A.
Right, where it tips. So that would be the weight of R times 1.5 positive, and the normal, nope, the normal is canceled out. The normal's canceled out, the frictional forces cancel out. P is 4 and it's negative. So I did the moment about A. It's the weight times 1.5 positive, and then P times 4 negative. And what does P turn out to be? Jordan?
Hold on. The weight of the fridge is 180. $67.5.
Correct. Okay, Maria, I'm going to go back to you because you want to know what all this, what it means, which totally makes sense. So in order for the refrigerator to tip, how much force does P have to be?
It has to be greater than 67.5.
Right. So now let's compare. If the man pushes at 45, it slides. If he pushes at 67.5, it tips. What's going to happen first?
Sliding.
Sliding is going to happen first. So let's go back to the question. The question said, can the man move the fridge by pushing? Is the answer yes or no?
Yes.
Yes. If so, does the refrigerator slide or tip?
Depends on how hard he pushes it.
Well, we just calculated 2 P's, right? So which one?
Don't we have to work with the second body to figure that out?
No, but we will. We don't need to actually, but the only reason we're gonna go to the second body, the person, is because I'd like to know if he's gonna slide or not. But right now, we just analyzed the refrigerator. We know the refrigerator is going to move. And as long as the man pushes at 45 pounds, it's going to move by sliding.
Uh-huh.
Okay, so now you have to also, those of you who are in materials or took materials, you know the difference between a static and a dynamic load. Who has not taken materials yet? Or who is not in material? Okay, so a dynamic load is this. It's an instantaneous punch. A static load is a gradually increasing load. So if I take an eraser and I pull it and pull it and pull it, that would be static as it stretches. Dynamic is if I just pull it and rip it. And you could realize that if you have a piece of taffy and you pull taffy slowly, it's going to stretch forever. But if you take a piece of taffy and you snap it, it's going to just break instantaneously. And you had to apply a larger load to get it to snap for a dynamic load. If this guy is like a football player and he runs up to the refrigerator with a large, huge load of 80 pounds and smashes it with a dynamic load, the thing's going to tip. Okay, but we're talking about moving refrigerators or around your apartment. Okay,
So then the key is that the sliding happens first, and that's why
yes, sliding happens first because the load, because imagine if you're moving a refrigerator, you're going to lean on it, right, and gradually push it. So you're going to hit 45 pounds before you hit the 67.5, and you're going to move it in position. Okay, here's a question, Edgar. This is all dependent on where the P force is. What if the guy was pushing it much higher? What might happen first?
So that means you're gonna, if you push it higher, that's gonna create a larger movement because you're gonna have a higher distance.
And
so it will require the least amount of force to start tipping it.
So it's quite possible that you're going to tip it, right? And you know that intuitively, you've moved furniture around, you know, go down on the ground and push, right? Don't push up high. You don't want it to tip. Okay. All right. So now right now we could stop the problem. We don't have to do anything else because the problem only asked us about the refrigerator. But let's talk about the man. So we have a free body diagram for the man, right? And let's see if he moves. So Laura, I haven't called on you yet. So what equation do you want to do first?
I'm sorry, what was the question?
Yeah, I'm doing the man now.
Okay.
What equation do you want to do first to solve for something?
Some of the forces in the Y.
Great. Sum of the forces in the Y is NM minus WM equals 0. The normal is 150 pounds. Okay. Laura, I'm going to continue asking you.
Okay.
In the other problem with the refrigerator, the second equation I did was the friction equation because I knew they were asking about the refrigerator being about to move. When the refrigerator is being pushed by the man, I don't know whether the man is moving or not or about to move. So I can't I can't use the frictional force. Okay. So what's the next equation I could use?
You could probably do the moment, but.
Well, I can't because all the forces are acting in the same line. There's nothing, right? There's no width. We're assuming this man is thin. So what's another equation I could do?
Just on the man, just the sum of the forces in the X.
Right, sum of the forces in the X equal the frictional force of the man minus P equals 0. So let's put in, because we know it's going to slide first, let's let P equal 45 pounds And that means the frictional force of the man that's going on right now is 45 pounds. We'll go over this because this is a little confusing. So we did the sum of the forces in the X, and I found that, and I let P equal 45 because that's what's going to happen first. Tipping's going to happen first. Hang on. I'm sorry, sliding happens first. What the hell am I talking about? Sliding occurs. So since sliding occurs first, I'm going to put in the 45 pounds for P, and I'm going to get a frictional force of 45. Okay? And now I'm going to do my friction equation. It's equal to mu of the man times N of the man, and that comes out to me 0.6 times 150. And 150 times 0.6 is 90 pounds. So what I did is I calculated the frictional force in two ways. One, I did the sum of the forces in the X with the force of P, which I know what is going on. And I got a frictional force of 45, which means the force that's between the man and the ground when he's putting a force of P on it, it is 45 pounds. But let's go bond. What does this one mean? When I calculated the frictional force based on mu N and I got a value of 90 pounds, what does that mean?
Well, that's just using the weight of the man, so I'm guessing that's when it's static, or
Well,
I mean, like when he's not about to move.
Not about to move. Good. Both of these are from static equations. He's not
Right.
moving in either case. But because the frictional force is used when in motion is about to occur, it means that the frictional force has to be above 90 pounds before it's going to move. The P force that's being applied has to overcome this 90 pounds for, that's a better way of saying it. In order for him to be pushed backwards, he has to apply a P of 90 pounds. And if we want, we could go ahead and do that. We could say, let me do this. Sum of forces of X is the frictional force minus P equals 0, which is 0.6 times 150 minus P equals 0. This, so either what I did first is I did sum of the forces in the X and found what the frictional force was due to the P that was being applied. And then I also solved for the frictional force by using the friction equation. All this, I did two equations, but I probably maybe should have just done this. Do sum of the forces in the X, which I did up here, plug in the 0.6 150, and I get a P value. This might be a better way of doing it. It means that in order for him to move, he's got to apply more than 90 pounds. If he doesn't apply 90 pounds, he's not sliding backwards. I think this is a better way. So let's cross this out and say P needs to be greater than 90 pounds for the man to slide backwards. I should say to the left. To left. I think this is a better way of doing it rather than having to compare two numbers, because in this problem, we were already calculating P. We calculated a P of 45 to make the refrigerator slide. We calculated a P of 67.5 for the refrigerator to tip. And then we had calculated a value of P that would cause the man to slide backwards. Okay, questions?
Could you post a scan of that?
Yes, I will.
Nice.
I'll post this.
Yeah, this problem is different than other statics problems because we have multiple states, I guess.
Yes.
So like you can write down, for example, FM, friction of man, but there's two values, right? So I don't know. Do we need to call those different things?
Yeah.
Like friction 1, friction 2?
Yeah, I think what I would just do is not do it, not
Just don't do
it.
that one. Okay.
Yeah, just calculate the P because
Okay.
you're finding the P for the motion. So friction, and I think I said this already, friction problems. And then the last topic we cover is the and equivalent systems. Equivalent systems, friction, and moment of inertia are the hardest. Now, equivalent systems, you guys got it really well. And I don't know what I did differently. I don't know, but so equivalent systems, I don't think you were as confused with as previous classes, but friction is hard. I mean, that first problem, we had to analyze the sliding twice. Here, when we analyzed it twice, we got a negative, so we knew it could only slide in one direction. And then we have this problem where the problem, we really didn't have to do the man at all because the problem only asked about the refrigerator moving. I just added the extra element. If there was another equation that said, is the man gonna slide? You would have had to calculate this. Okay. All right. So now we're going on to the last problem, which this is when I was gonna suggest we do a breakout room and you guys work together in groups. But if you want to do it as a whole, we can. It's really up to you on what you want to do. So what do you want to do? Okay, David said whole class. Mackenzie, whole class.
Yeah, let's stay together.
Okay, good. All right. And actually, when I'm in meetings and conferences, I like to keep everybody together too, because then I get to hear what everybody says, rather than just my 3 people. All right. Could you guys pull up a copy of the problem on the module so you could see it? Because it's kind of hard to see, but I'll read it. So I'm going to do the given. So given sketch info, and I'll read it. A force of 500 newtons is applied to the end of the cord, and it shows it on the problem, so I'm not going to write it in my given. It shows it in the sketch. Block A weighs 2,000 newtons, so I'm going to write that. Block A, the weight of A is 2,000 newtons. Block B is 4,000 newtons. The coefficient of friction between the blocks is 0.30, and the coefficient, I'm going to call that coefficient of AB. And the coefficient between B and the floor is 0.20. So let me show you how I wrote the given. The weight of the 2 blocks is block A and B, and then I used mu AB to represent the coefficient of friction between blocks A and B, and then mu B to represent the coefficient of friction between the block B and the floor. Is that okay? And I could post this too, okay? All right. Then again, let's get on to the confusing questions. A, determine if the system would be in equilibrium if P is equal to 2,500. I never ever, and there's a homework problem like this, I never plug in that number that they give me when they say if. I solve for P. And then I hate to use numbers that may or may not be true, right? I much rather solve for P and then compare it to 2,500 later. Does that, everybody understand that? That's another kind of trick with these friction problems. And then B says, determine the maximum force P for which the system is in equilibrium. Well, why don't they just ask for the P force, instead of confusing me with 2 different questions? So basically, what do I have to find? I need to find P. And then I probably will remind myself, because whatever I write in the find at the end of the problem, I always read the find again to make sure I answered the question. So I'm going to write compare to P of 2,500 newtons. So this is what I'm going to write, because at the end of the problem, I will look back at the find to make sure I answered the question. And I want to remember to answer that question, because if I just solve for P, I didn't answer part of the question. Okay, so let's practice drawing free body diagrams. Okay, those are like, typically, if you get the free body diagram right, you're going to get the problem right. So draw block A, separate. Draw block B, separate. Draw block A and B. Oh, wait, I'm drawing free, that's okay. We should do the table really, but let's draw the free body diagram since we're already in the mode. I guess just look up when you have it finished. And then if you're finished with the free body diagrams, make the table too. Could I ask a question while you're doing that? Which way is the frictional, which way do you think the direction is for the between block B and the floor? Between block B and the floor, which way is the block B going to move? How about Tim? You haven't answered yet. To the right.
To the right. Yeah.
So if the block B is moving to the right, which way is the frictional force B moving?
To the left.
Drawn to the left. Okay.
Yeah.
Okay, what about between A and B?
I said the friction force is going to the right.
On which free body diagram?
On A.
Okay, so let's look at block B.
Okay.
So block B is going to the right.
Yeah.
If block B is going to the right, the frictional force on both places are going to the left.
So it doesn't matter that the 500 Newton force is, I mean, on block A, because I totally understand block B.
Okay. So,
It's-
so first thing you do is look at the one that you're more comfortable with. Because P is pulling, and that's what the whole problem is about, is P. We know block B is trying to go to the right. So
Mhm.
that means either block A is staying seated on B and not moving at all, or block B is being slipped out from A.
Okay.
So on B, which is the thing that's about to move, we have two frictional forces going to the left. And therefore, block A's frictional force has to be an equal and opposite. Okay, so here's block B. The impending motion is to the right. P is to the right. So the two frictional forces are going to the
Yeah.
left. And I'm calling this one B alone, and I'm
Mhm.
calling this AB.
Okay, we're saying the same thing.
Right, exactly,
okay.
Tim, we're saying the same exact thing. I'm just explaining it again. So
Got it.
then on block A, you have to put this frictional force AB equal and opposite drawn on B.
Got it.
So I'm going to hold this up for a little bit. So notice any variable that has to do with B and the floor, I'm calling sub B. And any variable that has to do with B and A together, I'm calling AB.
On the FBD for block A, why did you draw NAB twice?
Because I didn't know. Because
Oh, okay.
didn't see
Oh,
that.
okay.
Sorry.
On
Good job.
on your B
Yeah.
diagram, from the top, you've got normal down. I
Right.
just put weight. Couldn't that just be weight A?
No, and that's something that when you come out of physics, almost every single problem you've done in statics, the normal equals the weight.
Yeah, yeah.
But look at block A.
Oh, it's being pulled up a little bit. Okay,
Yeah,
it's being pulled
the
up.
normal is not equal to the weight, so you have to be very careful.
Huh. Okay. Yeah, yeah.
Okay, does everybody see that? So you only draw the weight if the body is there. So when the blocks A and B are together, you draw both weights, weight A and weight B, because both blocks are there. But when you're drawing block A, you only draw weight of A. And when you're drawing block B, you only draw weight of B. Because the normals aren't always equal to the weights.
Got
And
it.
then here's my table. Amani, I haven't called on you yet. How many unknowns are there?
5.
5 unknowns. So how many bodies do I need?
Well, 2. If
2
it keeps-
bodies, right?
Yeah.
Now, we probably wasted a little time because I had you draw free body diagrams, although it's very good to have more practice in drawing free body diagrams. We only need 2. So 5 unknowns, 5 equations. We only need 2 bodies. Okay? Okay. Because we're talking about bodies and equations, I want to talk about the quiz you just took on Tuesday, which I haven't graded yet, but I have talked to a couple of people already about it. So give me your attention for a moment. The reason that I always have you pick the best equation that only has 1 unknown in it is to be efficient, right? It's all about time, right? So the least amount of equations you use, the quicker you could solve the problem. But remember that drawing free body diagrams takes time too. So if you could get 5 equations from something, but you need to take 1 equation from one of each 5 bodies, that's 5 bodies, 5 equations. That's going to take more time to solve the problem than if you took 2 free body diagrams and got 5 equations. Does that make sense? Right. So when you're thinking about efficiency, you want to think about, well, how many free body diagrams should I draw? What's the best free body diagrams to draw? And what's the most efficient equations? It just happens on the quiz, I had you draw all the free body diagrams, so you had all 5 of them. And then you could pick one equation from every free body diagram and be done. But it may be, and I'm not going to be grading the quiz hard, but let's say you had to draw 3 free body diagrams and you needed 6 equations. Is that so 3 free body diagrams, 6 equations versus 5 free body diagrams, 5 equations, which would be quicker to do? 3 diagrams, 6 equations, or 5 diagrams, 5 equations? What is the answer?
Less diagrams.
Less
diagrams, yeah.
So keep that in mind, right? Okay. But in the quiz and this problem, I asked you to draw all the free body diagrams because I want you to practice. But in the future, if you're trying to be efficient, it's a combination of how many diagrams should I draw? You know what? I don't think I'm recording. Am I?
You are.
Yeah, you are.
You're recording.
You're okay.
Okay, good. Yeah, Isaac.
Can I something that Tim and I have discussed is that, like, when you say you want us to do it in the most efficient way possible, like least equations, it will often take me longer to try and figure out the least equation way to do it than to brute force it and maybe use 1 or 2 equations I didn't actually need. Right. So it's like there's an argument to be made that it's sometimes a waste of time to try and figure out, well, what's the fastest way I could do this? Like, if I see that, great, but if I don't, it'll actually take me longer.
Okay, so fast forward yourself to being an engineer.
Yeah.
Right. Just think about when you're an engineer, do you feel like it's important to spend, I totally see what you're saying, Isaac. You could spend 20 minutes thinking about it when you could have just cranked all the equations out, right? Yeah. But now let's fast forward to engineering. Do you think you're just going to be cranking out equations, or you're really going to be thinking about things first? Really?
I think that over time we'll gain a better intuition. And so it will become, but I think that intuition is gained by chugging through. And then at the end, I'm like, oh, this is the quickest way I could have done it.
Right. Okay. So for this class, then maybe you could chug away, but make sure that you spend time at the end thinking back, because in the end, I mean, what I remember having, it's only about maybe 10 years now that I've been asking students to try to solve problems the most efficient way. Because what I used to get, hang on a sec. Yeah. Okay, great. Great, thanks, Mom. What I used to get is students would solve, let's say we had 2 3-dimensional bodies and 6 equations each, right? Now, 3D problems, you wind up having to crank a lot of equations anyway, but I'm kind of exaggerating, but I've gotten exams from students where they did 9 equations and 9 unknowns. I mean, 9 systems of equations, right? And it was just like, you could have done it in 4. And they weren't thinking. They were being a machine. They drew 1, did the 3 equations, did another, did the 3 equations, drew another, did 3 equations. They hadn't thought at all. And then they did a 9x9 matrix, when they could have solved it with 4 equations. And that's what I totally want to stay away from, because you guys are not, you're more interested in the understanding than just cranking through equations. Okay.
So there's a math reason why you can't always do that. So Isaac, if on the last couple of frame problems, I tried that just to see if I do every X and every Y, won't that work? Won't I get a big system that'll work with a giant matrix? And what happens is you get a bunch of equations that don't do anything. You get a bunch of equations that say like 0 equals 0, or like A equals A. And then they don't help you. There's no value in them. Right. So it actually is valuable to think about, well, if I do this specific moment, then I can solve something, right? Rather than just trying to robot through it.
Yeah, I'm definitely not arguing in favor of doing like every single equation. I guess I'm more thinking like sometimes I'll waste like 15 minutes like trying to see 3 steps ahead. And that's what I found to be useless. Like, where instead like maybe I'll do like 1 extra equation just because I couldn't see 3 steps ahead. So yeah, I guess we're largely on the same page.
Okay. Yeah, no, I like this discussion. This is good. All right, let's keep going now, okay? So we have 5 unknowns, 5 equations, and we said we need 2 bodies. So think about now what body do you want to do first? So let me give you a couple of minutes to just look at it, okay? And remember, we have some of the weight, so we probably should, instead of putting W's in the free body diagrams, we probably should put the values. And remember, the question is asking for P. So another thing I do in my free body diagram, you guys, is I circle P, because that's what I have to find. They don't care what the frictional forces are. They just want to know what P is. Okay, has somebody found an equation? Let me see who I haven't called on yet. Jason Lee, have you, looking at these three free body diagrams, have you found something that would be helpful? What are some
Can you
equations?
show me your third equation again? I mean, not the
third-
graph.
Yeah, the free body. So look at these three free body diagrams and what can you determine right away with one equation? There's a couple of things, I think.
Normal.
Okay, the normal. So which free body diagram do you want to use?
Use the entire one.
Okay, so what do you guys want to call that? You want to call it a free body diagram AB? Or free body diagram 1?
I usually just call it the full body.
Okay, full body? Okay. I think I'm gonna just call it AB, Tony, okay? Okay, so free body diagram AB. And what equation did you say, Jason?
The sum of forces in the y direction.
Great, so that's NB minus 2,000 minus 4,000 plus, and I guess I should have found the components of the 500, but I'm kind of just going faster through it. So it would be 500 times the sine of 30 equals 0, right? That's not good practice. Good practice is to solve for the X and Y components and do the checks. And I got NB to be, what did you get? 5750? No?
Yeah, that's what I got, Joanne.
5750?
Yeah.
Okay. So we did free body diagram AB, we did some of the forces in the Y, and we got the normal of B. Okay, Jason, I'm going to have you continue.
Yes.
Do you want to do another equation at AB?
Actually, the sum of y looks solvable because we already have the normal and we have the coefficient, so we can find y.
Okay, so tell me
not
what.
y from p.
Say that again, I'm sorry.
We can find p from the sum of the blocks.
Okay, so what equation?
The sum of forces in the in the x direction.
Okay, so sum of the forces in the X equal, it's P minus the frictional force minus 500 times the cosine of 30 equals 0. And Jason, since you're still on this, because they're asking us about P, and we know that P is going to move B, can we use the friction equation? Can we use the friction equation for the frictional force of B? Let me
Can you
ask
repeat the
you.
question again?
Yeah. So because we know that the problem is asking us to calculate P is in Peter, and that would mean that there has to be movement, can we say the frictional force B is equal to mu B times NB? Okay, wait. Before you answer, when are we allowed to use the friction equation?
When the thing it's about to move.
Right, is just about to move. And if we're calculating what P is, are we looking at things about to move?
Yes.
Yes. So can I use the friction equation?
Yes.
Okay. Okay, what did you get for P?
$21.58.
Okay. I got 1583.
I got 1583 also.
Oh, I might have messed something up.
Okay, so
That seems like the wrong coefficient. Wouldn't you want to use 0.3?
did I use the wrong one?
Because we're doing the whole diagram, so it's AB is in between them. My bad. I messed it up.
Right. Okay, great. So 1583. Got it? Okay, so now let's go back to what the question is. It said, determine if the system would be in equilibrium for P is equal to 2,500. Maria, if P is equal to 2,500 newtons, what would you say about the system?
I would say that it's not in equilibrium.
Not in equilibrium because it's moving, right?
Yeah, because
2,500 newtons is greater than the 1583. Okay, and then B says the maximum force P for which the system is in equilibrium. Maria?
that would be 1583 newtons.
1583. Okay, so now let's start from the beginning. Everybody with me? I had you practice 3 free body diagrams, but that's not really the process to go ahead and draw all the free body diagrams. The process is to find the given, do the find, and then do the table. In the table, is everybody listening to me or still crunching numbers? The table says there are 5 unknowns, and 5 unknowns says we need 5 unknowns means we need 5 equations and we need 2 free body diagrams. But that's only if the problem asked us to find all these unknowns. The problem only asked us to find P. We only really needed, if we think about this, they want us to find P. We really have one unknown in this problem. It's like one of those frame problems where they're asking you to find a small number of unknowns, but once you start using those free body diagrams, you have to introduce more. I have a question for you. How do you know? Well, that's another question. So in this case, we really only needed one equation to solve for P. So we only had to pick one free body diagram. Why, Tony, why did I pick, or why did you guys pick the free body diagram that has A and B together?
Because we could easily find the normal.
I was able to easily find the normal. And also I'm introducing less unknowns. It's like the frame problem where the best free body diagram to do first is the whole frame, because once you start separating everything, you have so many more unknowns. We got rid of the normal here between the two blocks. We got rid of the frictional force between the two blocks. So it's always best to do the whole body first. Once we picked that whole body, we were able to get the solution with just two unknowns and with two equations, and we're done, really. It's kind of like the refrigerator with the man. Once we analyzed the refrigerator, we were done, but I was curious whether the guy's going to slip back, so I continued. Are we curious as to whether block A will move or not? Maybe we couldn't give a shit. But if we did want to know, how would we go about finding it? So let's try it. We already answered the question. If it was an exam, I'd stop here because I don't need to, I would use my time for another problem. But in this case, so what free body diagram do you want to look at now? Danny, did I have you call on you yet? I don't think so.
No.
Okay, so Danny, take a look at these
Yes.
three free body diagrams. Which one would you want to do next?
For the block A,
Well,
what do we?
Okay, so we were just doing free body. Oh, this is the other thing. Danny, here's a question.
Okay.
How do you know by looking at this initial problem that you're not going to have to do any moments?
Oh, we're not given distances.
Right, no distances, no moments. Okay, so now we have these three free body diagrams. We've already exhausted free body diagram AB, right? Because
Yeah.
we did some of the forces in the X, some of the forces in the Y, and we did the friction equation. So the two free body diagrams left are A and B. Which one do you want to do?
Are we solving the problem again using these two free body diagrams?
What we're going to try to do is figure out whether block A is going to slip on block B.
Okay.
Kind of like what we did with the guy to
Right.
find out whether he's going to slip or not.
Okay. So then I would use some of the forces in the Y first.
Which free body diagram?
For free body diagram of A.
Okay, so let's see. Okay, let's do it. So free body diagram of A. We do some of the forces in the Y, you said, right?
Yeah.
So NAB minus 500
Yeah.
sine of 30. Great.
Yep.
NAB turns out to be,
Um.
I got 1750.
Yeah.
Yeah? Okay, so now we know the normal between. Okay, what else do you want to do next? Keep going, Danny.
Yeah, and then I did the sum of forces in the X.
In A?
Yeah.
Okay, sum of the forces in the X equal frictional force AB minus 500 cosine 30.
Yeah.
Equals 0. And what did you get for the frictional force?
433.
Yeah, 433 newtons.
Awesome.
This is newtons, right? Not pounds?
Yes. Yes.
Okay, so now what do you want to do now?
And then I went to the force body diagram of B.
Okay.
And then I solved for the forces in the Y, sum of forces in the Y, to get NB.
Okay, actually you could do something that's quicker than that.
Okay.
Since you chose to stay on A, let's stay on A. What can we do?
Oh, sure.
What's the third equation for A?
The friction equation.
Frictional force between A and B is
Yeah.
equal to,
Is equal to, well, the 0.3, is that what you're talking about?
0.3 times,
Times the weight, which is 2000.
not the weight, right? Frictional force is equal to mu times N.
Then the N, right? So that's 1750, right?
Okay. Okay, so my frictional force between A and B is equal to, 0.3 times 1750. Okay, so let me show you guys what I did. So Danny said to do free body diagram A. I did some of the forces in the Y, and I calculated what NAB is, the normal between the two blocks. I did some of the forces in the X, and I got the frictional force, the real force that's between A and B, to be 433. And then I went ahead and used the friction equation, which I know could only be in impending motion. I wrote down, if there was impending motion, the frictional force would be mu n, and I get a value of 525. So Maria, you want to tell me what that means?
That means
So I calculated NAB, the normal between the two blocks. I calculated the frictional force that is present between the blocks, that's existing right now. And then I calculated the frictional force that would be there for impending motion. And when I compare these two, what do I learn?
you see that the block isn't sliding because
Right.
the existing
So
friction
which block?
than the actual friction.
Right. So tell me,
The friction needed for impending motion. Sorry.
right. But talk to me about which block isn't sliding.
Block A.
Right. Block A is not. Block A is not sliding on block B. So this is just another problem that proves to you, you could only use the friction equation if it's impending motion. If you didn't solve for this equation and you went ahead and did the frictional you would have wrong answers here. I think that's what makes the friction, one thing that makes friction problems confusing. You really have to decide when you're asked the question whether there's impending motion or not. So what I'll do is I'll post all these two problems. Actually, I'll post everything. So I'll post, I have the problem. I'll post this one with the cylinder sliding up and how I got a negative. I'll post the refrigerator problem with both the refrigerator analysis and the man. And then I'll post the two block problem. Oh my God, I got done 2 minutes to spare. Okay, did I call on everyone? I think I called. Oh, Eric, I missed you. Eric, how are you feeling today? Tell me one thing you learned in class.
I don't know. You're putting me on the spot.
I'm going to come back to you.
Okay.
Angel, what did you learn today? Name one thing you learned.
Sometimes it's easiest to just draw the free body diagram for the whole setup as opposed to drawing free body diagrams for each individual piece.
Good, good. How about Victoria? What was something you learned today? Okay. All right, Eric. Tony, did I ask you a question? Yes, but tell me something you learned. You didn't have a long question. Where does the normal go? Where does the normal go on a refrigerator when it's about to tip?
Oh, that. Normal goes at the point of contact, basically, when it starts to tip.
Great. And when you're going to analyze tipping, what equation do you use?
You use the friction or the moment equation.
Correct. Right.
Yeah.
Right. And if you get confused by the question, just solve the problem as you normally would. They're asking you really for the force that they're pulling something at. And then make sure that you look back to the find to make sure you've answered anything. What else have you guys learned? What do you want to add?
I would add that you have to compare the actual friction to the friction of impending motion.
Right. So don't use the friction equation until you know it's impending motion.
Is it fair? Is it sufficient to say like the friction from the weight versus the friction from pulling is what you're comparing, right? Because that would help me distinguish the two. And then the pulling would need to overcome the one from the weight in order for motion. Is that accurate or not? Maybe not.
Yes. Yes. That the friction that you could calculate, the friction you calculate from the friction equation is the frictional force you need to overcome because of the weight. Yes.
Yeah. That's it.
Or if there was another weight load on it, like if there was a snow load on something.
Sure.
You know, if there was another load. Basically, I would say rather than saying the weight, I would say the when you use the friction equation, it's the frictional force that you have to overcome for all the loads in the system, and they happen to be the y's.
Yeah, because it's from normal, so it's
Correct.
whatever's pushing down.
That's right.
And then
From the
what's
normal.
trying to move it is like the pulling.
Yeah, let's say that, and maybe that's what you said initially, that the frictional force is the frictional force that has to overcome because of the normal, which is a sum total of all the y
That's it.
forces. Where we calculated the frictional force that's coming just because of that P force. Correct.
Okay. Yeah.
Good way
Thanks.
of thinking about it. All right, you guys.
One more time.
Yeah. The frictional force due to the equation, the friction equation, is the force that has to be overcome due to the normal. And the normal is calculated from all the forces of y that are on the system. Where when we calculated the frictional force with just some of the Vx's, that was really only finding the frictional force that is being, that the block is experiencing because of the X forces. Let me say it again. So if we use the frictional force equation, the friction equation, our friction equation is equal to mu times n. And n is the normal. It's the sum total of all the forces in the y. If I calculate the frictional force by some of the forces in the x, that's only the force that's present due to that x force, which happened to be P. Okay?
Joanne, we could almost think of it as the one is the maximum frictional force that could be allowed, essentially, that it will actually produce, and the other one is actual of what's needed, because it's equal and opposite, right? So that's what's needed to keep it in equilibrium.
Good. So the friction equation is the amount of force that needs to be overcome to get it moved. When you calculate the frictional force with X, well, yeah, actually, that's good, Tim. When you calculate the value from the X, you're determining what force is present. It's quite possible that when you do some of the forces in the X, you get a P of 3,000, but the frictional force is only 2,000, which means this thing's gonna move. It's gonna fly. So some of the forces in the X gives me the frictional force value that is actually present. And the friction equation gives me the frictional force that needs to be overcome to get it to move. Yeah, I think that's really great. Okay, so you may have seen my announcement. I belong to the community college engineering. I belong to the engineering education statewide group, of course. And all the community college engineering instructors and the deans at the universities get together twice a year, and it's tomorrow and Friday. So I am not going to be in office hours tomorrow and Friday.
And tomorrow is Friday.
Oh, today and Friday. Thank you. So I will not be in office hours today and Friday. Thanks, Maria. And then next week, we're doing the interviews. I haven't sent out when you're interviewing, but you guys, I'm hoping that everybody replied already. And so they're going to start on Monday, and everybody will get different problems to do. But we're not doing frame problems. We're definitely not doing friction. We're not doing friction problems. A frame problem is really just a regular statics problem that has a 2 force member in it, right? So I feel like that's up for grabs. You could get a frame problem, because I'm going to run out of statics problems. I didn't bring 20 textbooks here. I'm exaggerating, of course.
Could you give us just like a range of homeworks to glance over, just so we are kind of primed on like, okay, this is about like what we're going to be looking at.
I would go back to the statics of particles problems. Those are going to be cake for you now. Then I would concentrate on the 2 homeworks that were statics. So what was that? What numbers were they?
I think that was all of them.
Well, yeah.
3D or no? 3D or no on the interview?
2D or 3D?
Either one. Okay.
Either one. So homework 19 and 20. So the statics of particles homework, which you're going to fly through. There's no moments in there. Homework 19 and 20. And what I would definitely suggest, which I have already written an announcement, last week, I went over in detail homework 19 and 20 with a video. So watch that video, because it'll just tell you everything. Then the frame homework will be extra for you to prepare for. And make sure you know the steps: given, find, table, free body diagrams, solve for components with checks, equilibrium equations, because most of the points you guys got wrong is that you did not have the steps. And I want you to go through the steps: given, find, table, free body diagram, components with checks, and then the equilibrium equations.
Are equivalent systems fair game for the interview?
No, I'm not going to ask about equivalent systems.
All right.
But practice moments. If you still feel like you're a little rusty on moments, you better practice them, because, so 3D moments are up for grabs. Okay. Questions? So I still owe you 25 minutes. Now I owe you another 10. There's no way in hell you're ever going to get the 35 minutes back. So, because I think it's more valuable for you to have me for extra time than for me to give it back to you. But, all right, good. Any questions? Actually, hang on a second. Oh, my date book's downstairs. I think my conference starts at 1. So if it starts at 1, I'm free now. I mean, I should go get lunch, but what time is it? Oh, it's plenty of time. How about this? Well, you guys, some of you have physics, right?
I have another class. I gotta go.
Okay. When does your class end? 12:30?
We don't have physics today. We have.
Oh, you don't?
But I have a different class. Yeah.
You guys don't have, oh, that's right. Physics is on Tuesday. All right. I'll send you an announcement. Let me go down and get you can wait for me to get my date book if you want. Actually, I think it's right here. Hang on. Yeah, it's right here.
I'm assuming anybody who wants to go can go at this point.
Sorry, you guys. Thursday is my department meeting. I have a department meeting. So I need to go see Carl now.
Okay. Thanks, Joanne.
So, yeah. Just send me a question via Canvas if you have a question. Okay, see you guys. Bye.
Thanks, Joanne.
Yep.
Take care.
Okay, bye.
Thank you.
Yeah, bye.